Rafiq,
على النبي.
j'ai eu le même problème que la semaine dernière, tu t'imagines?
Ah bon?
Voilà, c'est incroyable. C'est une coupure Internet, en fait. Hein.
À la fac ou chez toi?
Elle est chez moi, chez moi.
D'accord. Heureusement, bon, ça va, bon, déjà. أهلا بك ريم.
سلام شكون؟
ريم.
نكتب لك قاعدة. صباح ويلكم لاباس؟
ريم عمامي دورتها لينيزماريك في البروبا ما تحضرش.
والله لا وقتها جابي ان كور يا وسام والله هاكا كي يبدا عندنا ديزيكزامان الصباح يحطونا لي كور من 5 ل 7 اليوم قريت من 3 ل 5 باغ اكزومبل
مش مشكل ما عاملين كانيات
اي
اللي غيب يحط فيها
لا 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 كله الا وسام
وفي اخر العام نعملوا بها عشاء
اي سي سا.
Oui, non, il m'a envoyé tout à l'heure un message pour me dire qu'il attend le lien.
Ouais.
Mais là, qu'est-ce qui arrive? Attends, je lui envoie un Messenger. Ah, ok, ça y est. Mohamed?
Ouais, salut.
Salut. Tu peux partager tes diapos?
C'est à quelle heure, au fait, qu'on démarre?
C'est tout de suite, c'est à 3 heures, heure française.
Tu m'as dit 3h30 dans ton truc.
Ah non, non, ben écoute.
15h30.
Ok. J'ai dû.
Ah, je suis désolé. Bon.
Ok, pas de souci.
Là, je viens par hasard. Hein.
Heureusement que tu t'es connecté.
Ok. Tu vois mon écran là?
Ouais, c'est bon. Bon, ça se passe en anglais.
Ok, bien sûr.
Et donc, je te présente rapidement et je te donne la parole. Ok, on va attendre encore 1 minute et on démarre.
Non, mais moi, je suis là comme ça parce que je suis allé m'allonger un petit peu parce que je suis à la maison.
D'accord.
Et je me suis dit, bon, là, il faut revenir.
Bonsoir Mohamed, c'est Rim Amami si tu te souviens de moi, ancienne doctorante. Comment vas-tu?
Ah ben c'est super de t'avoir.
Ça fait longtemps.
Ouais, c'est génial. Comment vas-tu?
Oui,
ah, ça me
je
fait
bien.
plaisir
Des années.
Ça me fait plaisir de t'avoir au bout des fils. Là.
Oui, moi aussi. Là, je suis en Arabie Saoudite avec tout le monde, là, toute l'équipe.
Ah, ben c'est super, ça se passe bien.
Oui, 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 bien, merci.
Et Nabil est en Arabie Saoudite aussi.
Oui, oui.
Hmm.
Comment va Toulouse et l'IMT?
Ah bah, bon, l'IMT, je ne sais même plus où ça existe. Moi, j'y suis plus là, depuis
Ah,
longtemps.
d'accord.
J'ai créé une entreprise.
Ah, c'est cool. Tu vas nous
Ouais.
recruter alors.
Avec plaisir, ouais, toi, oui.
Merci.
Hmm. Ah ouais.
Mais ça fait plaisir, en tout cas.
Non, c'est sympa de t'avoir au bout des fils comme ça.
Oui.
Mais il faudrait qu'on te voit physiquement aussi.
Oui, oui, oui. Je vais te contacter et on va parler.
Ah ben écoute, ça sera vraiment avec le plus grand plaisir. Hein.
Merci.
On va peut-être commencer là, non?
Ok, on va démarrer. Ok,
Ok.
hello everybody. I'm going to make a short presentation of Mohamed Masmoudi. Mohamed Masmoudi is a professor at University of Sabathier University in Toulouse, and he's also the leader of a spin-off Adagos. Here, the slide, there is the logo of this startup. And this startup is working on modelization simulations for physical problem with the neural networks. And Mohamed Masmoudi have a PhD at University of Nice on partial differential equations, and Mohamed Masmoudi is specialized on optimization and numerical methods to solve a partial differential equation, especially with the finite element method. And he create a first startup, and he sold this startup to the leader of finite element code called ANSYS. And after that, he started to work on neural networks, and I think it's the reason that he created this new startup, Adagos. Okay, Mohamed, okay, you can start. If you want to add some words to describe your activity, I think it can be very useful.
Thank you very much, Nabil, for this presentation. Indeed, I am working on also on shape optimization and topological optimization, and this is the connection between shape optimization and neural networks. The connection is the topology. That means we are optimizing the topology of neural networks. That is the connection. Thank you for this presentation, and thank you also for your kind invitation. And I am really pleased to present this work to you today. Then I will just record. Do you see my screen? It is okay?
Yes, it's okay.
Okay. I will just say a few words about the topological optimization of neural networks. This topological optimization leads to parsimony, and after I will show some applications of these neural networks to dynamic modeling, because it is, there is a problem of instability with dynamic modeling, the catastrophe theory, and also there are a lot of things like that. And finally, we are able to master dynamic nonlinear modeling thanks to topological optimization and thanks to parsimony. I will end with a short presentation concerning a collaboration with ST Microelectronics. ST Microelectronics is the European leader of electronic devices. First of all, this is our neural network. Here, what you see is the application of the topological gradient to create a neural network. As you can see, any cell can be connected to any other cell. It is not similar to classical topology, because in classical topology, a cell from one layer is just connected to the cell of the preceding layer. Here, if your output is just a copy of the input, you can make directly a copy, and you are not obliged to make to copy this input cell 20 times if you have 20 layers. That is the basic idea of our approach. And this creation is fully automatic. You don't need any manual intervention of the user, because the topology is so complicated that then the user cannot help at all. And this is fully automatic. That means we put artificial intelligence between hands of people who is not familiar with artificial intelligence. Let us just from the there are three major steps and the history of neural networks. We started with shallow and poor neural networks. Here we have the revolution of deep and redundant neural networks, and here we have the new generation of neural networks, which called the parsimonious generation. Then let us go a little bit into the details. Here you have this classical redundant neural network. The algorithm performed by this neural network, if x0 is the input, we have a loop like that. Here at each step like that, you have a W matrix, and you multiply the state of this layer by W. You apply the function, the activation function F, and you have the values on the new layer. And the learning, sorry? Can I continue? There is a question?
No, I think.
Okay. Then we, for the learning session, what we have to do is to minimize the error. This is the error. That means the difference between the input of the output of the neural network and the target value, which I call Y. And we have to minimize this error with respect to W. And this is the classical way of doing artificial intelligence. And here, in our case, it is a little bit more complicated, because we have to deal with sparse matrices, and let us say ZY is the concatenation of all previous states, because W can operate on all previous layers. For this reason, all previous layers here are called, I call it ZI-1, and W operates on all the previous layers, and of course W is sparse. And Z is the concatenation of all previous layers. That is the main difference with the classical approaches. Similarly to the classical approaches, we have two unknowns. No, it is not similar. We have two unknowns here. We have W, the connection, and we have gamma. But indeed, gamma is really not needed, because the gamma is just the set of non-zero coefficient of W. Gamma and W contain almost the same information. Gamma is the set of non-zero coefficients of W. Then let us do a little bit of mathematics. This is what is called the Lagrange operator. What is the Lagrange operator? We consider our cost function J, and we consider at the instruction of calculation of the neural network. That means we consider this instruction as a constant. For people familiar with optimization, this can be considered as a constant, and in front of this constant we consider Lagrange multiplier, and this trace, the trace operator, is just the scalar product between matrices. That is the classical standard product, but in case of matrices we use the trace of the product of two matrices. Then lambda is the Lagrange multiplier. And lambda is also the back propagation of the gradient. If you say that the derivative of the Lagrange operator with respect to z is equal to 0, you obtain a system of equations which leads you to the calculation of lambda. And lambda is exactly what you compute when you proceed by retropropagation of the gradient. It is exactly the same thing, but it is presented in a different way here. I hope that it is quite clear for you. I said that lambda I is calculated by telling that the derivative of the Lagrange operator with respect to z must be equal to 0. That means the variation for the lambda that you calculate by retropropagation, it is exactly the same. The variation of the Lagrange operator with respect to z is equal to 0. This is the definition of lambda. And if it is equal to 0, we can use it to make topological optimization. I am going to tell you how it is possible. First of all, you can, if you consider gamma 0 and W0, since the x are calculated this way, these quantities are equal to 0. And at the end, the Lagrange operator is equal to the error, exactly to the error. For the z that you calculate using gamma 0 and W0, you have equality between the Lagrange operator. I am sorry, here you have L. I don't know why it is missing. Otherwise, there is no way to understand this slide. Okay, then there is a perfect equality here because these terms are equal to 0, because z, what is z? The z is calculating using this formula. Then this is equal to 0, and we have a perfect equality. And since the variation of the Lagrange operator with respect to z is 0, that means we can replace and this expression and the expression of the Lagrange operator gamma 0 and W0 by gamma and W. If gamma and W are close enough to the initial topology. That means, and this is our way to evaluate the error function without making any calculation. We have just to replace here the initial value by the new value. That we have only to do that. We replace any value by a new value of W, and we have this equality. This is our way to, this is our way to make a fast estimation of the error without recalculating the error, just by making local calculations. This is what is called the Pontiagin principle. That means if you want to minimize J, you just minimize the terms under this some sign. You have just to minimize term by term this expression. That is the Pontryagin principle. There is a paper. It will be published and the proceeding of an ECOMAS conference. I will send that to Nabil when it will be published in a few days, and all these details are in this paper. Let us continue with some industrial applications. No, before application, I am just telling a few words about redundancy. The state of the art is redundant because it imitates the human brain, and the human brain we have redundancy because the living brain there are lots of cells, and the living brain continue working despite this loss of cells. And the keystone of the state of the art is really the redundancy. Why? According to a paper of Jan LeCun, the famous Jan LeCun, local minima are not a problem for large neural networks. If you have a large neural networks, you cannot have a problem with local minima, because you can imagine the Hessian function. A local minimum means that all eigenvalues of the Hessian function are positive. But if you have a large number of parameters, the probability to have all eigenvalue positive is close to zero. And for this reason, you don't have a local minima problem when you have a large neural network. This is the first property, first consequence of redundancy. The second consequence is that you can use poor descent algorithm, poor optimization algorithm. You can use the gradient method. The gradient method doesn't work at all. Normally, it doesn't work. But think to redundancy, it works. Why? Because of the redundancy, you don't need to converge. You should not converge, because if you converge, you have you are facing overlearning. You cannot converge. You shall stop the learning process before convergence. And for this reason, the state of the art is using this stochastic gradient method. It works perfectly because you don't need to converge. Because the gradient method doesn't converge. And this is really the keystone of standard state of the art method is the redundancy. If you remove this redundancy, the algorithms are really designed for redundancy, and everything works thanks to redundancy. Then it is big data oriented. It is oriented to discrete responses. It uses high resources, and the normal process is to try to modify the topology and to try again until reaching the optimal topology or satisfying topology. Now, the parsimony. It works with small data. You can reduce it works with small data set. Why? Because learning is adjusting the neural connections. If you reduce the number of neural connections, you reduce the quantity of data that you need to adjust the coefficients, because you can see the data as equations and the learning coefficients as unknowns. And the number of unknowns and the number of equations are related, as you know. It works perfectly with continuous problems because thanks to the parsimony, we can go to convergence without any risk of overlearning. And then we can obtain very accurate results thanks to parsimony. If you are parsimonious, you can go further with the optimization or the learning process without any risk of parsimony. We reduce the quantity, the resources, because we are reducing the data also. It is automatic, as I said, because it is not possible for the human brain to find the optimal topology. And I will focus this presentation on dynamic modeling because you cannot, any lack of parsimony leads to a divergent prediction. We need really parsimony to make dynamic modeling, particularly, of course, on the nonlinear case. Now, I am going to present some numerical results. And at the beginning, we are collaborating, as said Nabil, with this leading company called NCIS. NCIS is the world leader in software and simulation software. They are providing Fluent. For example, it is a well-known CFD simulator. And we are collaborating together. And the first challenge, honestly, I was far from believing that it was possible to do that, to learn some dynamic, the nonlinear dynamic system. For me, it is out of reach. And I accepted to work on that because they are paying. And this is a valve. This is an interaction between valve, which is connected to the input by a spring here. If you have a spring here, and as you can see, there is an interaction between CFD and structural mechanics because there is a spring here. And I don't know what it is. Okay. This is here. You can see the first test case. This is the excitation, is the pressure at the input here, the pressure or the velocity. Sorry, it is the velocity. It is the velocity at the input here. We have two test cases for learning, and we have only two test cases. Sorry, we have only two test cases because at each time step we have data. At each time step we have a transition and then a new data. And for this reason, two test cases are more than enough to learn the process. This is the validation test case. Here we are learning the full solution. We started with the full solution, and the output is the full solution. Of course, we are using some SVD coefficient to compress the output, but we are learning the full solution. This was the first challenge. And then people from ANSYS, they asked me, okay, very good, but now is it possible to learn only the location of the valve? That's all. You don't have additional information. You have as a scalar as output. You have only the X position of the valve. That's all. You don't have more information. This is really very challenging because it is not obvious to learn from only one scalar. Here we have two learning test cases here, and here we have the validation test case. This is the learning test case. This is the second learning test case. And here you can see a good agreement between the position, the actual position, and the opposition that we obtained using our tool. There is a very good agreement, and there are some oscillatory behavior here that you don't have in the excitation. And this is really fascinating because I was really far from believing that this is possible. But fortunately, my partners, they don't have the same scientific education as me, and they were not aware about these difficulties. And finally, thanks to their support, we are reaching this kind of solutions. Now, let us. What is possible to do? This was a very important step in the progress of this project, because I said to myself, if it is possible to learn from some degrees of freedom of a simulated solution, it is possible also to learn from measured data. And the so created model is equivalent to a model derived from a 3D or 4D simulation. Yeah, that is possible. You just consider you consider a probe, a measurement somewhere, and you can make a prediction that is similar to the prediction of 3D solution, detailed solution. That is fantastic. I was really surprised. And I will say that the model that we are building using neural networks is even better than the 3D model, because the 3D model has to be calibrated. You know, there is only misfit between the 3D model and the real thing. And you are always obliged to calibrate the 3D model to get something that is similar to the real thing. In our case, the model gives the model comes from the data, and finally it is similar to it has a good fitting with a good similarity with the real thing. And I said to myself, okay, let us go with measured data. And we have a measured car player. I cannot say his name. He's working on a hybrid engine. That means there is electrical engine, and thermal engine, and both of them are connected by a rod, by a shaft. Let us say a shaft, and the connection between the two engines is very nonlinear, because there is a torsion damper. I don't know if you see what is a torsion damper. It is a nonlinear, very nonlinear thing. And we have to learn the torsion of the shaft. The length of the shaft is something like is 40 centimeters, and we can reach 40 degrees. I don't know if you see the torsion here. It is 40 degrees. That means it is a huge torsion, because it is 1 degree for each centimeter. It is really very huge. Here you have the input of the input data. That here you have the velocity of the thermal engine. Here you have we measured some torsion moment. Here you have the gear, and here you have another torsion moment. One torsion moment from one side and one torsion moment from the other side. Anyway, at the end we were able to learn the output. Here you can see red points are measurements, and blue lines are our model. We have a zoom. We can see that there is a good agreement between the model and the data. And At the beginning, they asked us just to calculate the number of torsion to estimate the fatigue. For people who know a little bit about mechanics, you needed to use a kind of rain flow model to estimate the fatigue of the shaft. But they are really very clever. They embedded the neural network on the car and using electronic power or power of electronic power, they can cut the electric engine when they predict a large torsion. When they predict a large torsion, they cut for a millisecond or something like that the electrical engine, and finally they avoid the large torsion just using what I call in French it is électronique de puissance. I think that in English it is electronic of power or power electronic. I don't know. They use the electronic to cut the electrical engine, and then this program is embedded today on the cars. Another application using measured data is it is similar to the previous one. With the same company, they had problem also with a turbocharger, and here the output is at the bottom, I am sorry. Here you have the excitation. For example, typically the excitations are the speed of the turbocharger, the speed of the engine, the temperature at the inlet of the turbocharger, the pressure at the inlet of the turbocharger. And here you can see this is the deflection. And this is called an asynchronous deflection. That means a deflection where you have an interaction between the fluid and the structure. And this kind of vibration causes damage for the turbocharger. And we needed to avoid that. You can notice that nothing here is able to predict this kind of behavior because everything is flat. Everything is flat. No way to predict just by analyzing the data that this will happen. But this happens because of the history. We need to remember all the past to be able to predict this. This is a zoom on the same area here. This is a zoom. Here you can see it is very noisy. The red, I think it is the measurement, and the blue is our prediction. But they have been told by the company that what is possible to do is to modify the speed of the turbocharger, the number of rotation of the turbocharger that can be modified easily. And we reduced the velocity, the speed of the turbocharger by 1%, that's all. No? When we estimate there is a risk of asynchronous deflection, or asynchronous vibration, we reduced the velocity, the speed of the turbocharger, and these are the results that we obtain. Here is the actual variation, deflection, that means the ground truth variation. This is the variation predicted by our model, and after the control, after reducing the speed of the turbocharger, we reduced the deflection. It is the same here, and also it is the same here. And today, our partner is embedding this model, the second model that we are embedding on the car. We are collaborating also with Continental for the control of a thermal engine. They are And they are also embedding one of our programs on their cars, not their cars, the cars of other people, because they are not building cars. I'm sorry. I am reaching the end of, I have only to present this test case. We are in contact with ST Microelectronics, and we have been told to, they provided to us this, this microcontroller, and they provided also a test case. It is a robotic test case. It is a grasp stability of hand robot. What is the quality of the grasp of a hand robot? We have 20 input parameters, and we have only one input. You can, the input output parameter is here, and this is a TensorFlow, not Keras, because this is a TensorFlow model, and this is our model. The size, we are reducing the size of the model by 1,000, and also we are reducing also the error, because you know parsimony is a measure principle of science, and Einstein said that everything must be as simple as possible, but no simpler. And for this reason, we are obtaining better results. That is not surprising, because here, if you continue the learning process to get better results, that leads to overlearning. It is not possible to get accurate results in the case of classical neural networks. Here we can compare the results. We have been asked by ST Microelectronics to run the program, because it is an embedded program on a robot, every 50 milliseconds. And fortunately, if you use the standard frequency of the microcontroller, it is not possible to run the program every 50 milliseconds. For this reason, we were obliged to increase. Nabil Hussein did this work, this fantastic work. He's a former student of Nabil. Okay, here we're obliged to increase the frequency of the CPU. The duration of the execution of the program is less than 15 milliseconds, but the duration of the battery, we are estimating this using ST Microelectronics tools. It is reduced to 10 days, but when using our tools, the duration of the battery is 24 times larger. It is 7 months and 22 days. I would like to say that the standard duration on standby without running any program is 8 months, 3 days, and 12 hours. That means we are reducing by 10 days the expected the life of the battery, when here it is reduced to 10 days. And we are reaching the end of this presentation. Just I wanted to tell you that we compared with TensorFlow. With TensorFlow, we make at least 10 tries for each test case, and we select the best one. And this is the average reduction of the error. If we compare our tool to TensorFlow, we are 7% better. But if we compare the size of TensorFlow and comparison with the size of our tool, the difference is really huge, because we are reducing by a factor 3,000 the size of the neural network. You can see all the 100 test cases here on this page, and there are 100 test cases. Okay, then as a conclusion, I am reaching the end of this presentation. As a conclusion, we are reducing carbon impact of AI. We are reducing the sets of data. Both of them are strongly connected. We are focusing on continuous applications. That means digital twins and application like that. That means most of applications and industry and health applications are oriented to continuous prediction and not to discrete. The state of the art is oriented to discrete responses because it is redundant. And when you are redundant, the accuracy is not a problem, because if you are higher than 1/2, you say it is 1, and if you are less than 1/2, you say it is 0. You don't need really very good accuracy. But if you are interested on accuracy when you are dealing with continuous responses, you need parsimony. One consequence of parsimony is dynamic modeling, and the other consequence is reduced the development time of AI models, because in literature they call that when you are making trial and error test to find the optimal topology. They are calling that R&D. They are calling that research. And a new paper from the Massachusetts University, recent paper, I mean, of the Massachusetts University tells that when you estimate the carbon impact or the energy consumption of an application, you need to take into account all the steps leading to the final neural networks. You cannot say, oh, the learning process is 1 hour, the duration is 1 hour. No, you need to consider the 20 trial and error that you perform to reach the final solution. We need to accumulate all the tentative to find the optimal solution. You need to take into account all the process and not only the last step. Usually people used to say, no, that the last to consider only the last step of the learning process. For us, the last step is the first step, and then we take into account the duration of the learning process. There is no ambiguity in our case, but with classical method, we should take into account the accumulation of all the trial of and the trial and error steps. Sorry. Thank you very much for your attention, and please don't hesitate if you have any questions.
Thank you, Mohamed. Is there some questions? No questions?
The chairman is obliged.
Okay, I have one question, but okay, Mohamed, just when you realize your neural network to solve partial differential equations. Okay, then to the learning process, your data is, I think, the geometry and for structure problem, for example, and the constraints.
Yeah. Please go ahead.
The input, I think, I mean the input, of course, yes.
In that case, I presented today only test cases related to dynamic modeling. And in that case, the input is very simple. Here the input are, we have, let us say, six parameters here.
Mhm.
Here the input is reduced to 1, 2, 3, 4 parameters. Two of them are constant in this case, but they are not always constant. Here, the input is reduced to this and this. We have only one input and this test case, but it is really a very complicated test case because it is strongly nonlinear test case.
And you mean, yes, you don't take into account the shape of the geometry then in your
no, I am just presenting this this test case, but we are taking into account the geometry and shapes. You are right. Here, this is called an excitation. That means it is a kind of boundary condition. This boundary condition doesn't modify the PDE. It is the same PDE. We are modifying just the excitation.
Okay.
But I agree with you. I don't have results concerning this, but it is possible to modify parameters. Sometimes we are obliged to modify parameters because when the parameters modify the PDE is not the same, then we have to take into account parameters. And we are doing that, but I don't have it is very complicated. It was very, very complicated to take into account steady state parameters. That means geometry parameters, material property parameters, parameters that modify the problem, that modify the equations. These parameters, we are taking into account these parameters, but unfortunately, I don't have any example to that. I didn't prepare any example on that, but that works. And we need that because a parameter can be considered as an excitation. That is possible, but that doesn't work when the parameter modifies the PDE. If it modifies the geometry, if it modifies the material property, we need to create a neural network adapted to these parameters. And and the artificial intelligence literature, this is called neuromodulation. It is neuromodulation. That means the coefficient of the neural network are controlled by another neural network. It is called neuromodulation. We need that. You cannot, it is difficult to use parameters as input of neural network. It is not for example, here we have, if you have 3 input and 3 output of your differential equation, if the size of your differential equation is 3, you need to, if your neural network has 3 input and 3 output, if you add two input for your parameters, that doesn't work correctly. In this case, and the dynamic test case, you need really to create another neural network that controls your differential equation. That means the coefficients of your differential equation must be controlled by another neural network which involve the parameters, because the model, your differential equation model, must be modified, must be controlled using another neural network. And the input of this neural network are the parameters. It is quite complicated. We suffered with this problem, and thank you for the question. It is really very complicated. And once again, I was really, I was far from working on this kind of problems because it is complicated. But thanks to our partner, which is ANSYS, they said, no, we shall do it, and we are able to do it, and we did it.
Okay. It's in the same order, a question, very similar question. I know that you make what you call
Digital twin, yeah.
Yes, digital twin model for scattering problem. And for scattering problem, do you mean that for if you try to solve harmonic problems, you need one neural network for one frequency, or your neural network take into account a range of frequencies?
This is complicated. This is a complicated question. This is really a complicated question.
But I thought that you did it, not you
Yeah,
don't.
we are doing it. We are doing it. But there are two ways. No, we are obliged to consider a frequency range.
Okay.
Even if we can split the frequency range and small pieces of frequency range, of the small frequency ranges, that's possible to do that. But indeed, and real, we are obliged to take into account the frequency. Why? Because if you have resonance, you cannot catch the resonance. If you want to catch the resonance, you need to learn over frequency range to catch the resonance, because we are working with measurement, we are working with data, and the data is never located at the peak of the frequency. And for this reason, we need to have a parameterization with respect to the frequency, and really I'm sorry. You need to work on a frequency range to catch the resonance and the peak. Otherwise, you cannot do that. And we are working on two directions. One direction is convolutive approaches. That means, for example, you have. I have an example in mind. You have some metallization of a patch antenna. And the metallization is for an arbitrary metallization of this surface. The goal is to obtain the response, the solution of the electromagnetic field. And the parameter is an image. The image is the distribution of the metallization. And typically we can do that. And we are obliged to consider that for a range, for a frequency range, to be able to catch the resonance, because in general you have some resonance.
Okay. Is there other question, please? No? Malik, do you have questions?
Yes, doctor. Actually, it's sometimes I understand something, but I lose when you come with the equations and something like this. Neural network, we know that. Can you back to the slides that?
Which slide? Sorry.
You show the neural network and the layers. So you see that the input cannot be a parameter, correct?
The input cannot be.
Okay. Just for the input to the neural network. So you have some inputs. I didn't understand that one. It's hard to be a parameter. You said something like this.
Yeah. I think, I hope that it is clear. If you are dealing with a differential equation, the number of input is equal to the number of output. You have, for example, 3 input here, 3 output, and you have differential equation to 3 input. For example, 3 and 3. Y prime is equal to f of y, and f is a map from R3 to R3, for example. And now you have parameters.
Yes.
You have parameters. You can add, you have 2 parameters. You can add 2 parameters here. You can do it.
Yeah.
You can do parameters. But this is not efficient. It is not really very good because in general, if you have geometrical parameters, you are modifying all the equations of your system. And for this reason, it is better to create another neural network here. For example, to create a neural network here, another neural network here. The parameters are the input here, and the output of these neural networks are all these parameters. That is the best way to because it is very difficult to deal with differential equation, nonlinear differential equation. The prediction is really very complicated, and because of instability and so on. If you have 2 parameters, you can add them here as input to your differential equation. That means y prime is f of y and p being the parameter. You can do that, and in which case you add 2 parameters here, but that doesn't work really properly. We shall, in this case, I am talking about dynamic modeling. In this case, you put your 2 parameters here, and what is the output of this neural network? The output of this neural network are the links of this one. When you modify your parameters, you modify all the links. It is exactly like when you make finite element method and you modify the geometry. Your problem is modified everywhere, and you need this modification. Well, if you solve the Laplace equation and you create a matrix and you modify the geometry, each coefficient of the matrix is modified, and it is needed. We need to do the same thing. That means we have 2 parameters here, and the 2 parameters control the neural network that gives you the output of the neural network are these coefficients. That is the best way to achieve the parameterization of a differential equation. I don't say that this is necessary for all applications, but for dynamic application, we need that. This is needed really, otherwise it doesn't work. And really we spent a lot of energy to get something working.
Okay, so the problem you showed before is the part in, I think in a car, that's maybe the transmission. Have you worked with the transmission?
The transmission?
Yeah.
What kind of transmission you mean?
The car transmission.
The shaft of the car.
Yeah, the shaft you already did, but I think I mean the transition.
No, not at all. We what we call in English, we call it in English the power train. What is the power train? I didn't have the opportunity to work on that. I know only on the engine, no thing about power train. No, nothing like that. Okay. I am sorry.
Thank you very much. Thank you.
Thank you for your question, for your interesting question. Thank you very much.
Thank you.
Okay, thank you, Mohamed. Is there other questions, or we can stop here? No? Mohamed.
Yeah, please.
Here, in fact, a real neural network can solve partial differential equations for direct problem, for direct problem, inverse problem, or control problem by the same way.
Yeah. Thank you for the question. It is very, very interesting question, really, because we are facing these kind of problems today. I prefer solving PDEs. It is easy to solve PDEs today because there is a clear connection between the output and the input. If you try to learn the solution of the inverse problem, this solution can be quite chaotic. And today we are working in collaboration with Thales Alenia Space. It's a satellite builder on the inverse problems. And we needed to take care because for the same data, you can have two different solutions. And we have to take care about that.
You mean that the instability that you have on your PDE, you add it on the neural network for solving your neural network?
Yes, exactly. With PDE engineer, you have uniqueness and uniqueness, existence, uniqueness, and stability. That is perfect. When you are solving an inverse problem, you don't have uniqueness, you don't have existence, and even you don't have stability. And that means the data is not coherent. And what is, fortunately, and this study with people from satellite, we had a kind of quality of the solution, the stability of the solution. Is it stable or not? Mm-hmm. And thanks to this index telling you if the solution is stable or not, we start by learning stable solutions. We suppose that stable means existence, uniqueness, and stability also. And after, we try to generalize when the solution is not really very stable. But in that case, the target is not the data. You don't say my output must be equal to that. No, you need to say if the inverse problem criteria is satisfied or not. It is quite complicated to explain that. That means at the end, the target shall not be the solution. If the input is some data, the output is the solution of an inverse problem. To deal with this kind of problem, you should first consider only data when you are sure of the solution. That means the solution is stable and so on. You start by learning that, and after, at the end, you can see if it works for non-stable solution, but the target should not be the data provided by the inverse problem. You should find another criterion you should see if you fit with the inverse problem data. I am sorry, it is quite the solution on an inverse problem is not coherent. Then you should start the learning process by coherent solution. If you have some coherent solution, you start using that. And after you finish the learning by applying the misfit to the data of the inverse problem. For example, I am sorry, I am going to give an example. You have some boundary measurements, mm-hmm. and you are solving an inverse problem. And the misfit is the distance to boundary measurements. This is the error at the end. Then for some cases, for some boundary measurements, you know that the solution is stable. You say, for example, you have measurement everywhere on the boundary. You have measurement everywhere on the boundary, and you can start the learning process using the test cases where the sampling where you have the data over all the boundaries. You start by this data. And at the end, you want to see if your neural network is working with data which is located on a small part of the boundary. There is a micro, open micro, and yeah, and there is an open micro, and I think that the person is not following the conference for this reason. Oh,
okay,
no, it is okay.
I close it.
Ah, it is you?
No, it's not mine. It's not mine.
Ah, okay. And then just in few words, your problem is to reconstruct some information from data located on the boundary. You know that the solution is quite stable when you have the data on all the boundary, you have all the data. You can start with this data. And after, at the end, and you learn the solution for this data. And at the end, you can check if it is working or not for cases where the data is located only on a part of the boundary. But of course, you should not consider the solution that you obtain. The data, the solution of your inverse problem is not relevant because it is not stable. But you should only compare the response of your neural network with the data located on the boundary, with the small amount of data that you have on the boundary. You should compare the solution. Otherwise, the solution provided by let us say that the solution is the response inside the domain, for example. You consider the solution and you verify if it fits with the data located on a small part of the boundary. The target is not the solution that you found by your inverse problem, but the target is the data of your inverse problem. I hope that it is clear. No, it is not clear.
But I'm really interested by that. Is there some papers that explain that, or it's open problem and there is no papers on that?
No, I don't know. I'm just discovering. I am really, what I am telling you is something that dates from last week. I am discovering that it comes from last week because I am working on this test case from Thales Alenia Space, and really don't hesitate. I will be very happy to discuss with you on about that.
Okay.
And it is quite. It is not easy. It is really challenging as a problem because you shall learn. You have an inverse problem. It is data and a solution of inverse problem. Solution is not stable. You start by learning solutions, stable solution, good solution. You are almost sure that the solution is good. You start by learning that, and you cannot go further. You can just check if the solution given by the neural network satisfies the boundary condition or not, when the boundary conditions are located in a small area, for example. That is the basic idea, but I will be very happy, Nabil, to discuss with you.
Okay, I think I will call you. I will call you. Okay.
Okay, I will be very happy because it is really a very interesting problem. I was surprised by myself to face this kind of problems, and it is not easy at all. And for this reason, for me, it is a very exciting problem.
Okay, I see. Okay, thank you very much, Mohamed. And
thanks to all of you. How many people are attending the meeting?
We were today. We were about 24 persons.
Oh yeah. Many people are attending the seminar.
And you know, there is some people from Lamsin.
Yes, of course.
Was here.
From Lamsin? Who is from Lamsin?
Now I think they leave the session, but there was بالحسن دحمان، راضية بسي.
Okay, fantastic.
رياحي
Ali, Hadi. No,
Hadi Riahi was here.
Hadi.
Yes, there was 3 or 4 persons from Lamsia.
Oh, fantastic.
And now there is a lot of people from Lamsin who are in Jeddah and Riyadh.
Yeah, like
attending to the
like Rima. Okay. Very good. Thank you for this kind of invitation.
تعرف محمد فهمي بالحسن نجلة فريح.
Oui, oui, bien sûr.
They are here. They are attending.
Sorry. Thank you very much for attending this seminar.
Thank you, Mohamed, for this talk.
Thank you.
Interesting.
Thank you very much. Thank you. Keep in contact, Nabil. I will be.
Okay.
Merci, Mohamed. Merci.
Thank you.
Thank you, everybody, to join us for this webinar, and see you next time. Thank you very much.
Thank you.
Thank you, Mohamed.
Thank you very much.